So I'm going to try to explain really briefly what my how my solution for exercise 4 works, which is a solution that does not require any fancy knowledge about Qiskit or not. It was purely intuitive. It was just an idea that I spontaneously had, and I thought it could work. And I think it's just worth walking through the mental process or just walking through the intuition for the solution. I'm not going to go into too deep detail in these. But basically, just because I'm not so sure if I have the time to recreate the full solution. I've got it, I think, stored here somewhere because I definitely have to recap a lot about the actual U3 gates. But the idea is that was that even the solution actually, or was it the solution? So I don't remember. So the idea basically was that so you're given the unitary gate, right? And then so how do you figure out how can you decompose that? So the the idea is to take a look at the problem from a different perspective, which is well, a decomposition. It's just try to approach it right with just a given subset of gates, not with whatever gates you want. And so in this case, we're given just two options: the U3 gate and the control X gate. And the idea here is okay. So how can we make a circuit that does the same? So I had this idea where I thought, what if so there's this concept called uncomputation, and I'm really bad at explaining things in the inside, so forgive me for this might be a bit chaotic. But the idea is, I just before starting the video, I was playing with these, and I'm actually have a new pen. I'm gonna try to because I'm playing with is this working at all or not? Doesn't seem to work. I don't have it configured, I think, here for that. But basically, with this pen, I can paint nice stuff and say, "Hey, hi." But I think I gotta configure this a bit. I haven't really set it up. Anyway, I might not use this now. The idea of a computation is the following. So if let's say you have a Toffoli gate, right? And let's say you want to implement a multi-Toffoli gate. So you want to implement a Toffoli gate with 3 control qubits. Now let's say you don't have that instruction in your scripting language or whatever, it's Qiskit or whatever, right? So one way to do it is you can use temporal qubits. So you can use kind of work qubits, intermediate qubits to say, okay, I'm going to use that qubit as now a result, sort of an intermediate result. So these are 2 of my inputs. And then, when those are both on, then this is going to turn on. And so my third input is these, right? So the idea here is the inputs are this state, this qubit, and this qubit. And then, so what happens is what you do is you end up with the result of a Toffoli gate. So how do you know that this is working well? So if I put our inputs into superposition, we're basically going to get a list of all the possible correct answers to these, right? So this is all zeros. The thing is, it's only 1 when everything is 1. Now the problem of this solution, if you realize, is that that actually depends on that work qubit as well in here, and so this is a problem because we might want to use that qubit later in our computation, and so if the problem is that if this qubit is used, it will probably mess up with these. What happens if I put a Hadamard in here? Yeah, you see, it just messes up the whole thing. And you don't want that, right? Because it's entangled. So what you do is basically what you do is you can uncompute this operation here, okay? Should be using a pen. So you can, let me try. Does this work well? It doesn't feel well calibrated, to be honest. So you want to uncompute these. And if you do, oh, I can't even do this. Oh, that's so nice. Okay, I gotta set that up. So now, if you pay attention, this qubit is always. Should probably have a shortcut. This is always off. So this means this qubit is not anymore entangled with anything else. And so if I now put a Hadamard gate in here. Okay, I'm stupid. That's not how you test that. That's obviously the same that I was getting before. That is the way. Oh yeah, no, that's the. It's got to do with measurements. Sorry, apologies for this. So let's imagine that we are not uncomputing, right? So I'm so bad at this. Good. So this is the pre uncomputation thing. So the idea here is that you I don't know why I'm spending so much time explaining all this. Actually, it's probably not needed. But the idea is if I accidentally measure these being 0, oh my god, here. So if this would accidentally collapse and measure to 0, it kind of spoils the rest of the computation because now I don't have any valid solution. Well, because this qubit basically is entangled with the other one. So if it gets measured 0, then it just spoils it. Whereas if I do this here, like that, pay attention, the valid solution is still here. Okay. So and that's because we have uncomputed, and so it's become independent. Now the idea of my solution is if we are able to uncompute, or maybe another way to think about it is to disentangle or entangle the qubits. We might be just close to a pretty good solution, because to be honest, if you think about this problem, if these qubits were not entangled, right, it would be fairly simple, right? It would just be probably four U3 gates, and we would be done, right? So how was that? Qiskit, unitary gate, unitary operation. Unitary gate. Unitary gate. I think that's the way I did it. Unitary gate. It's in Qiskit extensions. Should I import that? Import everything from Qiskit. Is this what I wanted to do, or is it not? Qiskit extensions, and so unitary gate, and I think I was doing something like the U gate is basically a unitary gate with U as a matrix. Can I do that? Data, yeah. And how can I turn Qiskit unitary operation? Can I just do that? I forgot about unitary gate. I think I can just say, I think I just do on. I think I can just say QC apply. I think I can just do like this, U gate. Apply unitary gate. Can I do like unitary gate control, quantum circuit, unitary gate? Can I do this? Definitely have to recap this. It's a shame I didn't keep my solution. Come on, Qiskit textbook. Can I just search for apply? Qiskit implementation. Apply. So, or just gate. No, gate, it's circuit. Sorry. Circuit, and it's apply. I think that's the way it works. Should be more confident with these things. Or is it unitary? Oh, unitary. Okay. Apply unitary gate. Okay, 2 qubits. Okay, so it's a unitary, and then I give it the U gate, and then I give it the 0, 1, 2, 3, and then what if I just so Qiskit visualizations, block vector, something like this, block vector. That's the way it's done. Come on, I just want the example. I just have a fish memory, you know. I have fish memory. Pauli gates. Oh, here we go. Here we go. So, good. Getting this backend, blah blah blah. QC gets the plot. Okay, but I probably have to import the visualizations. I think, right? Yeah, probably. Oh, chunks. Port Paul. Where is not defined? From Qiskit. Okay, here we go. So you can see that it's entangled, right? So the point here is if this was not entangled, then it would just be super easy because it would just be a combination of U3 gates to rotate the things so we take them back to the initial state and zero. Now it's not that simple. The reason I didn't get it in the first run is because I kind of didn't think that it doesn't have to work just for the initial 000 state. It has to work at least for 3 different dimensions, right? It has to work at least for the Z, for the X, and for the Y dimensions. And then it intuitively, that's the way I thought, and I think that's because then you kind of get all the computational basis possibilities covered. That's probably the wrong way to put it, but it's you get the full space defined. So exactly. So the way that I thought is like, how can you disentangle that? Well, then with the with uncomputation, right? So if I figure out which control X gates will disentangle, then I can't be that wrong, right? The thing is, there's only 4 qubits, and there's not so many combinations of gates that you can apply that will disentangle the thing. And then if you kind of try quickly, you can realize that you will realize that if you just do control X between 1 and 3, just randomly trying. This is literally guessing. Okay, so and I guess there's more than one combination that does that. 1, 2, 0, 2. Oh, okay. So you see, we've disentangled one a little bit, right? Because now it's not just a dot in the middle. So and you kind of keep trying, right? So the way that I did it, don't have the time to repeat the whole thing, but you probably can get it in under 2 hours. Or but the way that that it worked for me was with so 3, 1. So I did 3, 1. Yeah, so here goes a little bit, and then I did because so once you've got these, man, I'm so bad at explaining that, but the idea is once you've got them disentangled, you can start rotating them around, but you can also do this in between. So this is then 2, 0, 2, 1. Is this the right solution? I don't think that's the right solution. 3, 1, 2, 0, 2, 1. Let's try. QC CX 2, 0. QC CX21. There's no magic to this, but you can see that those control gates already kind of do a really good job. And so once you're kind of confident, and it might be like now if you try other combinations, you'll see that it does, and you can't disentangle them more. So it probably means that you still need to do some rotations here and there to then try to disentangle them. I don't know exactly. I have to admit, to be honest, I don't know exactly why this really works and so well. And I'm guessing for certain unitary gates it wouldn't work so perfectly. But that's the point. Now, the thing is, once you get everything back to zero, everything pointed up at zero, what you need to do is you need to reverse the order of those operations, because these are, you're just uncomputing. So if you want to replicate the U gate, what you're doing is you have to do it the other way around, right? So you have to kind of reverse those operations, so you get the same behavior like the U gate, right? And so this is the essence of the solution, really. Now, it's not enough to get it to work with just the initial state 0, 0, so taking the state back to 0, 0, 0. But it also has to work with the plus minus bases and with left, right, or whatever other the y observable basis. So now what was interesting is that as soon as you try and see what happens when you apply a Hadamard to all the qubits in here, so you see that the unitary gate does absolutely nothing to it, which basically means that whatever operations you come up with down here can't be, they must be rotations around the x-axis, because otherwise they would just mess up with that, right? So if it doesn't do anything in the state, it just means that that they're always sort of rotating around these axes somehow, right? Otherwise, you would get, after applying the unitary gate in here, you'd get a bunch of other stuff in here. So that's not what we want. Yeah, and basically the only thing that you're missing is to make sure that it also works for the for these ones. So for the other, so if you do now an SDG or a G, right, or an S, sorry, to 0, 1, 2, and 3. Okay. So it also has to work for these. And here we see that they're also entangled, right? So yeah, and basically the way that I got this to work is, if I remember well, I think. So let's see. Where does this solution take me? Now this is really messy in here, and I'm so bad at explaining things. This is really messy in here, and because what you want to do is you want to get them, in this case you want them to, you don't want them to be in state 0, you want them to all be pointing towards y, right? So that's what you want to do. Now what I would suggest is, if you just focus on one of those dimensions, then you try to correct in the other one. So that's what I'm trying to do now, is I'm trying to basically say, okay, so what happens if I just copy paste this thing? Does this actually give me what I want? So those are just rotations, and the only reason I did them this way is because I don't know how the U3 gate really works. So I didn't want to spend time looking at these, but you can compress them. So it's 1, 2, 3, 4, 5, 6, 7. I think if you do these, I think that works as well. NP, oh yeah, okay, so from import numpy as NP. Yeah, okay, so that kind of works. If I apply the, yeah, if I would invert, so that kind of gives me these, and if I, so that's approximating U already, so that was a good solution. Let me see, I can just do it this way, I think. So, and this is, this was literally done by trial and error. That's why I can't replicate that super easily. Okay, yeah. If I apply a Hadamard gate first, now what I want to make sure that happens here is those stay the same and stay the same because effectively all those U3 rotations are along the x-axis. Now, if I take a look at, if I do the same, sorry, if I now do an S-pi and S-gate, it's not, you can see that it's not really, it's not where we want it to be, right? It's not, those things are not pointing here. So I'll be totally honest, and the truth is, I got lucky, I think, that I just managed to, I think if you did apply something like this, or 2.0, like, I don't remember even which ones I applied, because I don't remember the final solution. But it just worked by adding two more, it just worked by adding, yeah, I don't know. It just worked by adding a couple of, just two more control X gates. Oh no, sorry, not here. I think I'm stupid because I should reverse that and I should apply to the beginning. Yeah, doesn't matter. That's the point. Is this is probably the worst video ever explaining the solution. It shows that I really don't even know how I got this to work. I'll definitely deep dive into this. Okay, out of this I want to learn two things. I want to learn more about the U3 gate, and I want to learn more about computation and stuff like that. Because I don't know how is it possible that the control X gates actually do the work that they show here. Yeah, but basically that's it. You're probably highly unsatisfied with my explanation at that point, but it really comes down to this. It's just purely intuitively just uncomputing, just taking a look at the state and trying to bring it back to zero, trying to bring it back to plus, and trying to bring it back to I. So to the sort of pointing, the, or is it minus I or I think. Just bring it back to the, basically to the different initial states in here. And once you get a combination of rotations that works for all of them, then you're basically done. And so, yeah, and I think I got a score of 55 finally. So it's not the best. I got one control, not too much, I think. But you probably can then tweak it from there, or try to find another initial set of rotations. That's my guess. Yeah, that's it basically. I'm gonna do. I'm gonna do probably another set of videos going through different solutions in here, because I think it can be interesting to see how other people solved it. And some people have really put in the actual effort, not like me, to keep everything nicely in code. So this person has basically gone through all the solution and is using transpile, blah blah blah. See, I mean, it's like that's what I wanted to avoid, is kind of try to go a bit of the formal way. But this is, I think, really well explained. I was taking a look at this yesterday. It's really well explained in here, the way this is done. But it's it literally took me 2 hours with a bit of luck. Okay, so no merit in this solution, to be honest. It's just I wanted to see what the intuition behind uncomputing actually really worked, and I'm happy that it did. So cool. Any questions? Just write in the comments below, and stay tuned for more content on these, because we've got a lot of other topics coming up soon. Cool.